Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at section 9.3 from your textbook, which basically runs you through some of the theoretical results that apply when working with linear systems of differential equations. Now, this is going to be another sort of short video because we're going to just state the sort of major definitions and theorems here without proof, because the proofs of each of these sort of theorems are almost identical to the proofs that we did that were in the corresponding situation for higher order linear differential equations that we did in chapter 8. Obviously, these are slightly different because now we're talking about systems of first order differential equations, but actually all of the sort of mechanics and the theoretical results carry over here. So we're going to take a little bit of time to talk about these results and talk about what they sort of mean, but we're not going to spend too much time going into the details of the proofs. This means also that this will help us sort of get to sections 9.4 and 9.5 a little bit more quickly so that we can actually see computationally how to deal with actually looking at some of these systems of differential equations. So let's look at a couple basic definitions and talk about some theorems here. So first of all, we're going to give a definition for what it means to talk about an initial value problem for a system of differential equations. So a vector differential equation of the form x prime of t equals at xt plus bt. Remember, since this is a vector differential equation, it's the same as a linear system of differential equations. We're just putting it in vector differential equation form. Along with the n constraints of the form x at some t sub 0 is a1, a2 through an. This is what we call an initial value problem for a vector differential equation. So notice that for a vector differential equation, when we give an initial condition, we have to give an initial condition for each component of that vector function. In other words, we have to basically say what x1 at t sub 0 should be. It should be a1. x2 at t sub 0 should be a2. xn at t sub 0 should be an. So when we talk about an initial value problem for a vector differential equation, you actually have to give n constraints. Okay, notice that that concept of n constraints is very similar to what we did when we talked about higher order differential equations. We said that if you have an nth order differential equation, you have to have n constraints. Usually that was a constraint on the function, its first derivative, all the way down to its n minus first derivative. The only difference here is that instead of having constraints on each successive order of the derivative, you instead have a single constraint on every component function of the vector function. All right. So our first theorem that we're going to state, again, without proof, your book doesn't even prove this one because, again, this is going to be an existence and uniqueness theorem, and that's really for a more advanced course. So this theorem states that the existence and uniqueness also applies to systems of differential equations. So it says an initial value problem of the above form, so something that it can be written in this vector differential equation form, as long as a of t and b of t are both continuous, then this is guaranteed to have a unique solution. So just like we said with higher order linear differential equations, that as long as all the components are continuous, or what we call regular, it's guaranteed that every IVP will have a unique solution. Same thing here. So provided that a of t and b of t are continuous, we're guaranteed that every IVP for a system of equations, a system of differential equations, is guaranteed to have a unique solution. Remember, this is a existence and uniqueness theorem, right? So this is an E and U theorem here, right? By saying that not only is it guaranteed to have a solution, right, the existence part, that solution will be unique. All right. Now, again, this next theorem is one that your book does run through a quick proof of, but we actually proved the identical situation for when we were talking about higher order linear equations. So again, I'm going to skip the proof here, but it relies on this existence and uniqueness. This theorem says if you consider the homogeneous linear system of n differential equations represented by the vector equation x prime of t equals a of t x of t. So notice we're saying homogeneous. So b of t is assumed to be 0 here. So we have a homogeneous system of differential equations. Then the set of solutions is an n-dimensional subspace of Vn of r. Remember, Vn of r is the vector space of all n-dimensional vector functions. So this again confirms, right, two important ideas. First, when you're talking about a homogeneous system, you are comfortable in saying that the solutions aren't just a set, they're actually a subspace. So they're closed under addition, closed under scalar multiplication, etc. Even more important here, it says that if this system consists of n differential equations, then the solution space is n-dimensional, meaning, as we'll see in section 9.4 and 9.5, when we want to actually figure out a basis for that solution space, we will need to find n linearly independent solutions, and then we know that all of the solutions will be generated by those n linearly independent. So this theorem is proved in your textbook. You guys can take a look at the proof if you want, or if you prefer, you can also just look back at how we proved the sort of corresponding idea when we said that the solutions to an nth order linear differential equation that's homogeneous was an n-dimensional subspace of C infinity of R. We actually went through the full proof of that. This guy's proof is very similar. All right. We also have a result about the Wronskian, right? This again mirrors a result that we proved in chapter 8. This theorem here says that if you have solutions x1, x2 through xn, and they are all solutions to the homogeneous linear system, x prime of t equals a of t x of t, then these are linearly independent if the Wronskian is non-zero for all t. Now, if you think about what we said in the previous video, we said that if the Wronskian is non-zero at a single value, then it's going to be linearly independent. This is an extension of it that strengthens what we can say about the Wronskian if we know that the vector functions we're examining are solutions to a homogeneous linear system. If we know that the solutions are, if they're solutions to a homogeneous linear system, then we're saying the Wronskian is either going to be always non-zero, which means that they're linearly independent, or always zero, which means that they're linearly dependent. So again, in general, the Wronskian doesn't tell you that. But if you have the extra piece of information that you are looking at n vector functions that are all solutions to a homogeneous linear system, then the Wronskian tells you everything you need to know. It's either always going to be non-zero, meaning they're linearly independent, or always zero, meaning that they're linearly dependent. All right, the final theorem, right, that mirrors something that we did in chapter 8, talks about how to solve non-homogeneous linear systems. Now, to be honest, in our course, we don't actually make it all the way to solving non-homogeneous linear systems, but I'd like to still state this result in case you guys ever encounter this in later courses, or in case you just want to read a little bit further into our textbook once our course is done. What this theorem says is that if you let x sub p of t, that's going to be the particular solution, is a particular solution to the non-homogeneous linear system x prime of t equals a of t x of t plus b of t. And then if you let x1 through xn of t be linearly independent solutions to the corresponding homogeneous, notice that this is the homogeneous because we've sort of deleted that b of t, then all the solutions to the non-homogeneous can be written as a linear combination of the solutions to the homogeneous plus that particular solution. This, again, even though we're not going to prove it, should be very sort of clear or believable because we had this exact same theorem when we were talking about higher order linear differential equations. This is actually what we used when we introduced the method of annihilators and when we introduced the method of variation of parameters. Right? This is saying that if you want to determine all the solutions to a non-homogeneous system, you just need to find a single particular solution and then use any linear combination of the homogeneous solutions plus that particular solution, and that'll generate every one of your solutions to the non-homogeneous. So, even though we aren't going through and proving each of these theorems, you should see that each of these theorems can be matched up to something we did in chapter 8, because a lot of the theory that applies to higher order linear differential equations applies to systems of first order differential equations, and these results all confirm that. In our next video, we'll be moving on into section 9.4 to see computationally how we generate these x1 through xn that form the basis for the solution space of a homogeneous system. Once again, we'll be sort of starting that focus by looking at what happens when we have constant coefficient systems. Just like how we started when we were working with higher order linear, we started with the constant coefficient situation. So we'll take a look at that in our next video.